with the momentum of that particle. And for the tachyon, it's just the exponential term. And for the gauge boson, there is a little derivative here, and the vertex, and the polarization vector psi mu here. And then for the graviton, it is here where the polarization vector is denoted by epsilon here, need to be symmetric and tasteless. Okay, but every vertex operator are proportional to this exponential here. What different is the derivative of the field and the polarization vectors. And it depends on what theory we are working on. If we consider the open string, the vertex operator needs to be inserted on the boundary of the worksheet here, as you can see here. I insert just only two, but it can be n of them. And in the core string, the vertex operator can be inserted in the bulk of this worksheet. And of course, you can interpret between this kind of two insertion. If you consider the scattering between coarse and open string, you need to insert the core string on the inside of the in the inside of the worksheet, and the open string on the boundary. Okay. So, and then to consider the expectation value, we can evaluate the products of vertex operator by using the weak contraction, or with the certain name is called OPE, or the operator product expansion. And the weak contraction of the space-time field is here, this guy, equal to minus of alpha prime over 2 times with the metric tensor of the space-time, which in this case is flat. It is a flat space-time, and time with the green function. And the green function depends on 2 points of this field. And of course, the green function depends on the topology of the worksheets as well, sigma. And by using this weak contraction, we can use this as a basic to calculate the expansion of this exponential, the product of 2 exponential. Okay, which is proportional to the exponential of the Sij times with the green function, where the Sij is basically the product of 2 corresponding momenta, Ki and Kj, and as I said, G is a green function. So if we consider at the simplest version of the worksheet, for the core string, the topology of the worksheet can be considered as the sphere. So, I forgot to mention that this exponential is called the Koba-Nielsen factor, and this factor will appear in every string amplitude we are going to consider, because as I said that every vertex operator are composed of this exponential term. So that means this term will appear in every scattering amplitude, string scattering formula. Okay, for the topology, and if our worksheet have the topology of the sphere, the Koban-Nielsen factor turns to be just simply the absolute Zi minus Zj to the Sij, where Z is basically the complex variable of the complex plane, because we can project the S2 on the whole complex plane plus the infinity point. Okay, and Zi and Zj are labeled the point of the inserted vertex operator on that complex plane. And then if we consider if our worldsheet have the topology of a disk or the D2 here, the Koban-Nielsen factor is basically probably the same, but instead of Z, it turned out to be X, where X is just the boundary of a boundary value which is real, and because we consider the topology of the disk, it can be mapped into the upper or the lower half of the complex plane, so that the boundary can be thought of basically the real axis. So, which in this case I represent it as X, which is the real axis value. Okay, next. So that means the general expression for the endpoint scattering amplitude at 3 levels are, okay, the first line is the amplitude for the core string at the endpoint. You can see that there is in terms of integral, that there are endpoints of coordinate to be integrated over the complex plane. The Zi, as I said earlier, it is the coordinate of inserted point, and this guy is the Koban-Nielsen factor, and the function k and k tilde here is the correction of kinematic factor. We depend on the external state. Okay, if they are taking on the k and k tilde is just 1, but if they are like graviton or higher excited state, it's involved kinematic terms, and it's also involved the polarization factors or polarization vectors as well. And here, the volume here is the volume of it is a gauge volume, and in this case, it is SL2C, which is the Mobius transformation on the complex plane. Okay, which here, the volume here is allow us to, because it is a Mobius symmetry, it allows us to fix 3 points, any 3 points on the worldsheet. So instead of integrate all the set or the point Z and Z bar from I from 1 to n, so you just reduce it by 3. And the same go for the open string amplitude as well. But for the open string, the integral are on the real axis. You can see there are n of them here, and this guy is the actual Koban-Nielsen that I mentioned earlier, and with the correction of kinematic factors, sorry. And the volume, the gauge volume is SL2R, which allow us to fit any 3 points on the boundary. And there are special names for this expression at 4 points. So at 4 points, the open string is well known as called the Veneziano amplitude that I presented to you earlier. It is basically the beta function. And for the core string, The 4-point amplitude is called Virasoro-Shapiro amplitude. Okay. So next, I'm gonna talk about the mathematical aspect of the string amplitude. As I mentioned earlier, that the string amplitude is rich. The string amplitudes are rich on mathematics, especially there is a research area that interplay between string scattering amplitude and the number theory, which involve a lot of mathematics, which as I said, it involves a lot of number theory. And I will provide you just a basic example of it, which is the Veneziano amplitude and the Virasoro-Shapiro amplitude. And the Veneziano amplitude is basically the 4-string scattering at 3 level, which is the beta function here. And as the beta function, you can expand it in terms of as the series, in terms of, as you can see, in terms of the Mandelstam variables here to the power n. Here, this is the series that can be expanded. You can see that as the expansion goes, the coefficient of this expansion is basically this Lima zeta value, zeta n here. So, and in closed string, if you expand it in the same way, you can see that the expansion go in similar way. You can see that the expression of this line and the lower line are approximately the same, but in the closed string, there the summation cover just only odd terms. So which the even term disappear. Okay. So as you can see in this example, even at the simplest situation of string scattering amplitude, which is the 4-point, this string amplitude encodes the special function in mathematics, which is called the Riemann zeta value here. And from this aspect, a mathematician have the conjecture between open string and closed string in mathematical way. You can see that the expression is kind of very alike, right? So, and this conjecture is called the single value map. So if you map the theta value of the open string, or if you do a single value map, the open string amplitude will turn to the closed string amplitude in that conjecture. Okay, because this map it negates the even term of this theta value, leaving only the odd term and multiplied by 2. Okay, so it is a basic example how string scattering amplitude can interplay with mathematics. And just for the general knowledge, so there are some number theory that's involved in the string scattering amplitude. As I said earlier, for the genus 0 or at 3 level and n equal to 4, the coefficients of that expansion involve the Riemann zeta value and the and the closed string is of course the Riemann zeta value, but with odd terms, but just only the odd value. And the conjecture between open and closed string is via the single value map, where it's cancelled or is nullified all of the even zeta value. And for the higher point, the string scattering amplitude give what is called the multiple zeta value, which is the generalized version of the Riemann zeta value. For example, instead of one input of n, it can be arbitrarily more input, like here 3, 5 or whatever it is. And for the cos string, you can see that it is a single value map of this spatial value or single, or it's called single value mzv or multiple zeta value. And at genus 1, the spatial function is called the elliptic multiple zeta value, and for the cos string is called the modular graph forms, where there is right now there is, if I recall it correctly, there is no known single value conjecture, but the evidence is quite clear that these two guys can be related via the single value conjecture, but it's now in the process of ongoing research. Next, apart from the mathematical aspect, I'm going to talk about the aspect that the string scattering amplitude can be related to the field theory amplitude or the actual field theory. So it's both realized that in the limit where the alpha prime go to 0, the string scattering amplitude reproduce the field theory amplitude here, or you can see in cartoonish picture here that the string scattering reduced to just the Feynman diagram, which it means a lot of Feynman diagram, but I didn't draw it here. And to translate into words, which it means that the string scattering amplitude is equal to field theory amplitude plus some string collection, which depends on the alpha prime and higher order of alpha prime. And of course, we have a lot of string theory to deal with, so it's reduced to many field theory counterparts. For example, if we working on the bosonic open string, the field theory version is the Yang-Mills theory, and of course for the cos string is the field theory is the Einstein-Hilbert action, and open superstring is super Yang-Mills, and closed superstring is supergravity, and of course you can consider both open and closed string called the mixed string amplitude, and it's reduced to the scattering of the gravity and the gauge boson, or in field theory is called Einstein-Yang-Mills theory. And as I say that this appear as the limit of alpha prime go to 0, but string theory suggests that there is a string collection part which depends on the order of alpha prime. Okay, so let me give you an example on the 4-point superstring amplitude for gluon. This is the simplest formula for the 4-point superstring theory. It can be written as the amplitude of 4-point super Yang-Mills theory times with the string terms here. The kinematic term here is the Sij here is involved, the alpha prime is high alpha prime inside, so this factor or this chunk here is the string correction. If you expand this, you can expand it. If you expand it around the alpha prime and Sij, when alpha prime go to 0, this guy is basically 1. But if you consider the I would say the Taylor expand around the alpha prime go to 0, this is the first order of the expansion, and this can be seen as the correction of the gauge theory, which is as there's two S term here, which is that means our correction is in the order of alpha prime square, and the correction is known as the quartic term correction, which is the F4 theory. Okay, so what I would like to say that the string theory can provide correction to field theory, and there is here are some known string correction to field theories. So if you're working on the open bosonic string, it provides alpha prime correction as a F cube theory to the Yang-Mills theory. And if you consider the bosonic whole string it provides the alpha prime of the R square and R cube to the I action. Okay, and if you consider the open superstring, it provides the correction to super Yang-Mills theory up to the alpha prime square here, and then for the closed superstring, it provides the correction to supergravity at the order of alpha prime cube, as the R to the fourth, or the R is the Ricci scalar. Okay, but by the way, the R and R4 R cube here is just the it's just the simplest modification. It can be involved like the Riemann tensor as well with the same order. Okay, so next I'm going to talk about the aspect of the string scattering amplitude on the structure. I mean, the string scattering amplitude can provide a structure between amplitude, and this structure can be very elusive in the aspect of the field theory viewpoint. So, for example, there is a very famous known structure called the KLT relation, with name after Kelvin, Lavalin, and Tye. The KLT relation relates to amplitude together, which is the closed string amplitude and the open string amplitude together, and expect the closed string amplitude as the open string amplitude square. And because the closed string contains graviton or gravity, and the open string contains gauge particle, which means in field theory limit, it can be considered as we can construct the gravity as the square of the gauge theory. And I would say that this relation is hardly to see by the field theory viewpoint, because the quantum version of the Einstein gravity contains infinite numbers of interaction vertices. This is the graviton interaction vertices. There are infinite number of them, but the Yang-Mills interaction for gauge boson are just 3 and 4. There are only two types of vertices, which is 3-point interaction and 4-point interaction. You see that these two theories are very distinct in the viewpoint of the usual field theory, but from the inspection of the string theory, it can be related via this conjecture, the gravity as the gauge square, or in the research area, they call it double copy, because the gravity is the double copy of the Yang-Mills theory. So to prove this, it has been proved by consideration of the costring amplitude, and I will not show you how to derive it in general, but just only for the first non-trivial case, which is 4-point amplitude. So the trivial case would be 3-point, but the 3-point amplitude is basically constant. So it needed to consider. So I'm going to show you how the costring amplitude, at least at 4 points, can be factorized into products of two open string amplitude. Okay, and as you can see, here is the expression, the Koba-Nielsen expression for 4-point costring amplitude here, and you can see the integration is on the complex plane here. The set is on the complex plane, right? But there is one integration, because as I mentioned earlier, the volume of the Mobius transformation allow us to fit any 3 points of the inserted vertices. So in this case, I fix the point, each t point at 3 different points. So and the traditional choice would be fix 3 points as the point 0, 1, and at infinity. Okay, and to transform this guy to the open string, and as you may remember that the integral in open string need to be integrated over the real variables. So in this case, I can rewrite the set as basically x plus iy, and z bar is x minus iy, where x and y are real, right? But right now, the integrand z here and 1 minus z here will turn into x and y variables here. And if we would like to make all of them real, if we would like the integrand real, that means we need to deform the contour integral of y here, because it has a complex value here, right? So I need to deform y. Which originally from minus infinity to infinity as c1 here. I need to deform it into integrate over the imaginary axis here, which can be done by using this map here, and I need to shift a little. I need to shift a little, for that y will not integrate over. For that y is not integrate on the imaginary axis totally, because there appear a branch point on the complex axis. So to avoid that, I need to shift the contour a little by epsilon chi here. Okay, by doing this, and we express the x plus y and x minus y as a new variable called psi and eta, the integral turn into this kind of integral. And you can see that the integral is integrate over just only the real part, just only real, the psi, because x plus y are real and x minus y are real, so the psi are integrated over the real axis. Now, which is very pretty likely the integration of the 4-point open string now. But in order to integrate, we need to take care. We need to take care the branch point, which is occur in here as that there is branch point at near 0 and near 1 and near the point 1 here, and the branch point are shifted in the imaginary axis by small amount of the value delta here. And okay, to evaluate the integration of the eta, so we need to consider the different value of psi here. So in this case, I consider the 3 different values of psi, where psi less than 0, where psi are between 0 and 1, and where psi larger than 1. And it turns out that to avoid all the branch point, the eta integral, for the first part, the eta integral needs to be deformed around the branch point in the lower half plane. Okay, similar to the third one, the third region where the psi greater than 1, the eta contour need to be deformed in the upper half plane, and for the theta value are between from 0 and 1, the contour of integration of eta need to be deformed upper and lower of point 0 and 1 respectively. And you can see that if this integral is well defined at infinity, so that means the eta integral can be closed at infinity. So for this example, the first one can be closed in the lower half plane, and there is no pole in the lower half plane, so that the integral is 0. Similar to the third one, to the third case, we can close the contour in the upper half plane, and by the Cauchy theorem, because there is no pole and the integral is well defined at infinity, this guy is vanished as well. So what is left is this region, the integral in this region. So, which means the non-vanishing term is the integral of psi from 0 to 1, right? And this guy here is basically the beta function, right? It is basically the beta function where it is the open string amplitude, but here is subject to certain ordering of particle. Okay, and what is left is to determine this amplitude here, and the amplitude it determines this integral here, and this integral, as I said, the contour integral is at this red line here. Yeah. So it allows us to either close the contour on the upper half or the lower half, right? So if we close the contour in the upper half, so that means the contour are deformed to just the contour of integration from minus from infinity to 1 and close around 1 and then travel from 1 to infinity. Okay, and if we cause the contour in the lower half, it means the contour are allowed to deform from minus infinity to 0 and then go around the point 0 to the lower half plane and then integrate from 0 to minus infinity. And then by avoiding the multi-value of the integrand, we need to set up the branch cut so that the integrand here can be written for the upper half plane. The integrand can be written as this guy with the phase factor here, and similar to the similar to the contour that closing in the lower half plane, this integrand can be written as this guy and corrected by phase factor here. All in all, by some after some calculation, you can see that this integral here will turn to the open string amplitude with the phase factor correction, and that phase factor can go to will transform to this factor here. In this case, it's basically sine function of the kinematic terms here, sine 1, 2 here. And this is the basic example of how the KLT relation was derived. And for general n particle, this is for 4 point here. For the general n particle, we can make the analogy to the 4 point and translate it into more points. So the cos string at n point will be proportional to the product of two open string amplitude with certain ordering rho and tau here, and there is a phase factor function here which depends on it depends on alpha prime and it depends on rho and tau, which is and it's basically if you look at the expression, this s here, the function s here is basically the product of sine function of the kinematic terms. Okay, and of course, when you restrict yourself to the field theory limit or the alpha prime go to 0, this amplitude, the cos string, if you consider the graviton scattering, this cos string turn into the theory of gravity, and the bosonic and the open string part turn to theory of gauge boson, or we could say Yang-Mills theory, and square of it, which namely the double copy. Okay, the next structure that I would like to tell you is called the color kinematics. Okay. First of all, there are the linear relation between color order open string amplitude, which is in string theory is called monodromy relation. This is the modern name, but in prehistory string version is called the Platt identity, which is discovered in 1970 or around that time, which is very ancient relation. Okay, and this because and as I can say, as I said, in field theory limit, if we limit alpha prime to 0, this provide the linear relation of the color order field theory limits called the BCJ relation, and this BCJ relation is relatively new comparing to the string counterpart. So you can see, and the fact that the string theory version came first is kind of surprised me, because the field theory was developed longer than the string theory. Okay, but you can see that the fact that the string theory gives this kind of relation first suggests the more simplicity of the string theory. Okay, this is the way how you prove the monodromy relation by consider the integral, this kind of integral, which is very similar to the open string amplitude. Here there is the Kobayashi factor and the correction of the external state here, but I apply certain ordering to the xi coordinate here. In order to have the monodromy relation, you integrate one of the coordinate, I would say x2 from minus infinity to infinity, but you need to implement, in order to integrate it, you need to implement the suitable phase correction to the monodromy relation to avoid the multi-value issue of the integral. So it appears that if you integrate this and close the contour, and by closing the contour, the Cauchy theorem tells us it will be 0. And there is a phase factor here, phase factor that due to the phase correction. And in field theory, in field theory limit, this exponential turn to just basic ki dot kj. Here, this is called the BCJ relation. Okay, let me finish the talk by give you some summary. So the basic idea that I would like to express here, that there are many areas in string theory amplitude would be very interesting. First of all, it can be related to field theory amplitude directly in the field theory limit, or the alpha prime go to 0. And a part of that, it can give you some correction to the field theory according to the string theory. And in mathematical sense, it interplays with the number theory that I mentioned earlier, which is it can give you Riemann zeta value, multiple zeta value, modular graph forms, and etc. that need to be considered in the future. And it will give you an underlying structure among amplitude, which is the double copies, or the KLT relation, and the color kinematics, or the BCJ relation. And obviously there is many more aspects that I haven't mentioned in this talk, such as it can be related to pure spinor formalism and ambitwistor string, which is the field theory amplitude that use the technique from string theory to formulate. Okay, and thank you for attention.
Okay, so If you have any problem, you can ask online by Facebook or YouTube. We can check. Okay, so I saw some question, but oh, okay. So it's from Darius Samad. Do you mean the Kn function can represent the Riemannian sheet in the complex plane of the amplitude?
So I would say that the cobaniusan factor, or as you say, the cobaniusan function, depends on the Riemann. This guy, right? This guy here. It depends on the topology of the Riemann manifold here. So, for example, if the topology is this sphere, this cobaniusan go to here, and if it is go to here. So I would say that different Riemannian manifolds give different cobaniusan factors. So for the genus 1, it would include it would include more information of the topology, which include for the torus, it would include the what is called the tau, which is the parameterization of the torus as well. So in higher genus, that means the Cobaniusan term would involve the topology of the worldsheet. So the integration is not just the integration of the coordinate. It would be involve the integration of the model, what is called the moduli parameter as well.
Okay, so he continued the problems about what is the physical meanings of the poles in the complex plane of eta zeta.
Physical meaning of in the complex plane. Physical meaning of I'm not sure what he talking about, the pole in this eta and psi, or probably here. Generally, I would say that the general expression in the Cobaniusan formulation is consists poles, right? It consists pole. Like for example, even at 4 point here, it consists many poles because the gamma function contain poles in when the argument is 0 and less than 0 are negative integer, and that pole can be interpreted as the intermediate state of the particle exchange. For this example here, if this pole it contains S and T pole here, and it can be and when the gamma function are at the pole, is the gamma function turn into like 1 over alpha s here minus some integer, which signify the fact that it is the propagator of the particle, which is the intermediate particle. So generally, the poles suggest the intermediate exchange particle, right? And for the string, there are infinite series of intermediate exchange particle.
So he continued, in the sense of KLT, one can represent the two-gauge boson exchange 4-point box diagram instead of one graviton exchange 4-point tree level. So is his understanding correctly?
In KLT sense, one can represent two-gauge boson exchange. Okay, the box diagram instead of one graviton exchange 4-point diagram. I need to mention first that the KLT relation was derived at tree level, but at loop level, to be honest, I'm not sure that if that is hold in loop level or not. So and by the way, I think you have the picture that the graviton exchange that in your picture, I assume that you mentioned that there are like two metal particles and exchange graviton in the box diagram and go out with two external particles, and at tree level it's two particles and exchange the graviton and then go out, something like that. But the KLT in the KLT picture, I believe it's more like the pure gravity scattering or the pure graviton scattering, which can be compute or view as the square of the pure gauge scattering at endpoint. In that sense, if you involve the metal particle as well, I'm not sure if it still holds. So maybe I cannot answer your question. So probably my answer is the KLT relation hold for purely close, right? Yeah. So in the sense of gauge as in the sense of gravity as gauge square theory is, in my opinion, it's like the pure graviton scattering and pure gauge boson scattering. It maps between purely close boson, purely graviton scattering and purely gauge boson scattering. And in field theory is like the purely Einstein-Hilbert and purely Yang-Mills, or super symmetric orbits. Yeah, I'm not sure if you're satisfied with my answer.
Okay, so if you have further questions, you can still write your question on the Facebook page or on the YouTube channel. And so let's thank our speakers again and ending this seminar. Okay.